Ale.
Okay, hello everybody. Welcome to the seminar. We have today Manuel Szewc. I hope I pronounced correctly your name, from the University of San Martin in Argentina. He will talk about tops, in particular Bayesian inference for tops at the LHC. Please.
Thank you for the organizer having me. As Juan Antonio said, I want to talk about Bayesian inference for four tops at the LHC. This is a work that we are hoping to submit to the archive in the next few weeks in collaboration with Ezequiel Álvarez, Barry Dillon, Darío Farughi, Yernay Kamenik, and Federico Lamagna. What I want to talk about today is the following. First, I will give a brief reminder about why we are interested in four tops and why we need to improve on our current understanding of the process, and then I will give a brief an insight about how we can model this problem and how we can infer the parameters we are interested in a Bayesian framework. I will talk about how we can model the data, how we can perform this numerical inference and show some results for a specific benchmark, and then give a brief set of conclusions that point the way towards a more semi or unsupervised framework for extracting four top signals at the LHC. So four tops at the LHC is one of the last benchmarks of the standard model that we are very interested in probing. It's been the target of a huge experimental effort and has achieved impressive results. There are a lot of recent results on a lot of channels, monoleptons, multileptons, two leptons same sign, two leptons opposite sign, and each of these searches targets a specific final states and has a specific strategies that introduce some systematics due to the current uncertainties on our theoretical understanding of four top physics. So let me give a brief review of why four tops is complicated per se. It's a very populated partonic final state. We have a hard process of 2 to 4 particles, so we have a lot of kinematical information. And we have to introduce the additional complication that the top decays and the W decays before reaching the detector. So we have a very populated final state with a lot of B-jets, a lot of decay products of the W. These decay products will dictate the final state we are interested in. For example, here we have two jets, a lepton, and it introduces a lot of information which makes it difficult to reconstruct the underlying hard process. For instance, here we have missing transverse energy in two W's, so it's very hard to reconstruct. And it makes it harder the fact that we have also to include initial state and final state radiation. So we have a lot of jets, a lot of B jets, a lot of some amount of leptons, and this introduces very hard to reconstruct kinematics and also uncertainties in the modeling. To do this, to match the need for theoretical input, there have been a lot of state-of-the-art calculations, a lot of improvements over the standard model predictions. For instance, in this very interesting paper by Frederick Pagani and Saro, they find that the next to leading order corrections are large, which is already very important to create samples for comparing with experimental data, but they also found that they need to take into account the mixed corrections because they are comparable to pure QCD ones. And so the theoretical calculations, which are necessary, are very expensive. And they find a very interesting large accidental cancellation between next to leading order terms involving mixed couplings. And this cancellation has a very clear scale dependence, which makes it very, very hard to assert how beyond the standard model physics could change the results, the expected value of the cross-section. So there is a need for very expensive simulations, which maybe are needed for every possible kind of beyond the standard model. let me show in this case how this theoretical uncertainty creeps into the experimental search. I will show it with a monolepton and two lepton opposite sign search, where the uncertainties are related to the background simulations, TT bar plus jets. And we see that there is an excess on the measured data for large number of jets. It is attributed to a mismodeling of the backgrounds. And so there is a fitting which takes into account the heavy flavor uncertainties, and they extrapolate from different control regions to have a better understanding on the background. And they introduce additional systematics. So we face the situation where we want to disentangle signal for background, but we don't understand neither the signal nor the background very precisely, because at large number of jets, it's very hard to have a precise simulation. So we are very interested in four tops. Here I mentioned some of the possible, of all the work done beyond the standard model effects in four tops, because four tops is one of the last still allowed windows into beyond the standard model physics. And so we are very interested in being able to find the signal appropriately and to find any possible excess over the standard model predictions. So let's focus on one specific channel, which is the one I'm most interested in, which is the two lepton same sign and multilepton channel. In this channel, the main backgrounds are TTZ, TTH, and especially TTW, all accompanied by a heavy flavor. And the backgrounds of the signal here are of the same order of magnitude, which is really important because we are able to extract the signal more easily. A nice thing about this final state is that the multi-jet complexity is really reduced, but there is another complexity because now we can't reconstruct the leptonic W so precisely, so it's a very challenging final state. And when the collaborations perform the measurements, they find, CMS finds something along the lines of the standard model cross-section, which is of order 12 femtobarns, but Atlas measures a central value, which is twice as large as the standard model prediction, and which is consistent with the monolepton results. We have to keep in mind that the result is still compatible with standard model predictions, but that this uncertainty should be reduced in order to be able to tell whether we are something anomalous or not. The main sources of uncertainty we need to tackle when trying to find four tops is that the high multiplicity of final states are very challenging to simulate. There are also many backgrounds which are data-driven, which are obtained through data-driven techniques. And there is a consistent set of discrepancies in TTW, where there is a need for rescaling the measurements because of an excess in the number of events that are charge asymmetric and that have charge asymmetry and high Bjet multiplicity. So this is also very interesting because there is at least there could be a mismodeling of TTW. There could be something we are not able to tell yet, and so we need to have a better way to test our theoretical predictions. Also, there is the problem that there's not a whole lot of events, which makes it challenging when implementing very sophisticated algorithms to find the signal. So what should we do? Well, the ideal scenario is that we have to improve our knowledge of four top and its irreducible backgrounds, mainly TTW, but doing this is very challenging because to obtain the cross-sections and the kinematical distributions, we need to perform very expensive simulations, which are really not that easy to be trusted because we need to extrapolate from other control regions to know whether our simulations are done correctly. The other way is maybe going to a lesser Monte Carlo dependency So we can learn from the signal region directly using semi or unsupervised or supervised techniques, which is the idea I want to talk about today. Let me give a brief comment about machine learning at the LHC. Machine learning is ubiquitous at the LHC. There is a vast amount of boosted decision trees, deep neural networks, which are very common in experimental searches. But there has been a recent search of semi and unsupervised algorithms applied to LHC physics. Here I point towards some general bibliography, the living review of machine learning techniques, the LHC Olympics and the Dark Machines Anomaly Score Challenge, where we see some examples of applications of algorithms which are trained with a large dependency on labeled simulated data. Among the many possible applications, the one we are most interested in this talk and in this work is how to enhance LHC analysis by reducing the systematic of Monte Carlo simulations. This in turn will allow us to perform beyond the standard model searches, reduce, although not eliminating completely, the necessary model hypothesis. So what we want to do is to learn 4 tops. So we will focus on this two-lepton same sign, and we will choose to focus only on the total positive leptonic charge and consider only 4 tops and TTW, just for testing the algorithm. We could easily include TTZ and TTH either as different topics or as the same background as TTW. And we see that in this channel we have roughly one-to-ones where we have a similar signal to background event ratio. So we want to focus more on the technique than in the simulation dataset, which is obtained through the usual pipeline of MATLAB, PT, and Delphes. And so what we want to do is to include our imperfect modeling of the physical processes as prior knowledge and improve and update our knowledge using the measured data. We want to adopt a Bayesian framework that can build upon the Monte Carlos without relying so much on them. So we choose when we want 4 tops, we choose the low level observables that drive the discriminatory power. The previous work has shown that the 2 main observables are NB and NJ. We tested with other algorithms that this is indeed the case. And we decided to focus only on the number of B jets and the number of light jets and to keep things simple. And so what we will do is to consider a probabilistic mixture model where each event is generated by one of the underlying physical processes. Because we cannot observe the class assignment, we call it a latent parameter, which we call seed. So for each event, we will measure one possible value of light jets and one possible value of B jets because of the cuts we introduced. This could be 4, 5, 6. This could be 2, 3, or 4. So to model the probability of a single measurement as a mixture of 2 processes, background and signal. This is easily achieved by writing the likelihood of said measurement as the sum over the latent variable cell. So what we mean here is that the probability of a single measurement comes from the probability of having a TTW measurement and the probability of said measurement given that it's coming from TTW, and the probability of having a 4-top measurement and the probability of said measurement coming from 4 tops. So as I said, the probability of 4 tops can be easily obtained by the signal to signal pass background ratio, which we call pi1. The probability of TTW is the complementary one, and the probability mass functions are the ones we would ideally obtain from simulation. We can model this because we have integer variables as a multinomial, where we have two multinomials, one for each process. And so we have a matrix of dimension 2 times the number of possible jet measurements, times the number of possible B-jet measurements, minus 1 because of the normalization constraint. So the problem is that we don't know any of these parameters. A frequentist approach would roughly obtain these parameters using a maximum likelihood fit. It could even fix the probability mass functions using Monte Carlo simulations. But we're interested in a Bayesian approach, which is roughly to treat the parameters as random variables with prior probability, and we need to update the probability with the data encoded in the likelihood. So what we need to do is to write the well-known Bayes theorem. So we're interested in obtaining the posterior on the parameters by obtaining the likelihood of the data, the prior, and the evidence, which is the main problem when performing Bayesian inference. So we know from the modeling that we can write the likelihood in the following way. So we need to specify the prior distribution for the gamma matrix, the prior distribution for the pi, and doing this and computing the evidence, we can have the posterior. So the problem when we will try to do this is that we have a lot of parameters to infer. We have the ones that I talked about and the fraction, but we only have one measurement per event, so we don't have enough information to disentangle signal from background. We don't have enough power to get the proper mixtures right. So we can solve this by assuming conditional independence between Nj and Nb. That is, we assume that if we know the class, that is, if we know if it comes from TTW or for tops, then the probability of sampling J and B is simply the product of the probabilities. They are conditionally independent. So we model the probability of measure a light jet J given the class T as a multinomial with parameters alpha sub T, and the probability of measurement B given class T with the multinomial with parameters beta sub T. So this is the key hypothesis which allows us to perform inference and find the mixtures. What we are assuming is that all correlations between Nj and Nb will come from the fact that there is a mixture of processes. So we need to learn the mixture to learn the correlations. If we were performing supervised search, this would be the very simple naive Bayes algorithm. So what we have to emphasize is that it's very different to consider conditional independence than to consider full independence. It's not true that they factorize. So here there is a sum because we are marginalizing overall class labels. So if you write the likelihood, now we have the following likelihood because introducing the expressions for the multinomials, we have the sum over possible labels, that is TTW and for tops, the probability of sampling an event from said class, and the probability of each measurement given said class. If we consider this likelihood, we are assuming a specific covariance matrix between the light jets and the B jets, which can be written in the following form. And so we see that we need to have mixtures to have correlations, and we see that there is the product of up to 4 different random variables. So if we have probability distributions for each of these random variables, we will have some very general correlation matrix. So we are not constraining it. We are still being very flexible when trying to find the correlation matrix. So now we are reducing our number of parameters from this one here to 2 times the number of possible light jets plus the number of possible bit jets minus 2 for each normalization constraint, plus 1 because we keep the fraction. And the Bayes theorem will now look like this. We have the posterior over all parameters, the likelihood, and now we have a prior for the fractions and a prior for each of the alpha matrix, each class, and for each of the beta matrix. So now we do model the priors. To do, we will consider the conjugate prior of the multinomial, the Dirichlet, which is a very general distribution which has very nice properties. It makes very easy to perform what we need to perform next. So the Dirichlet has a set of hyperparameters eta, which dictate the distribution, and we will map our prior knowledge to the Dirichlet hyperparameters. We will take advantage of the Dirichlet flexibility to describe what we know about the parameters. So what we said before is that the Monte Carlo simulations usually are taken to give estimations on the parameters we are interested in, pi, alpha, and beta in this case. We will consider that instead of giving estimations of the parameters, the Monte Carlo simulations will give expected values under the prior distribution. So we can parameterize the etas, the hyperparameters, as a probability distribution times a normalization factor. Here P is the parameter value estimated through Monte Carlo simulations, and this total scaling factor will encode our confidence in the prior estimations. This can be seen by looking at the mean and variance of a given possible outcome that follows a Dirichlet distribution with this parametrization. We see that the expected value is nothing less than the one given by the Monte Carlo, but the variance is related to the one given to the expected values given by the Monte Carlo and is controlled by this sigma parameter. We also could compute the covariance between measurements. There's a lot to play with here. So now we have the likelihood, we have the priors, and we can put everything together as a generative process that helps us understand four tops. This is how we are modeling the production of events in the two lepton same sign channel with positive leptonic charge in the four top searches. We can draw it with a plate diagram that encodes the generative process. We are modeling the events to be obtained from distributions which are sampled from some priors and which are then used to sample a class assignment, and given this class assignment to sample the conditionally independent measurements. Here we list it as equations, and this for every event in the sample, which we assume each event is independent, so the likelihood is the product of the likelihoods. The thing is that if we want to learn for tops, that is, if we want to perform an inference and obtain the posterior distribution on the parameters, we cannot do it exactly. The problem is that the evidence is intractable because there are a lot of possible assignments, and thus there are a lot of possible updates on the prior, and keeping track of them all is very challenging. Luckily, this is a very simple modeling, which is already very common in the literature. So there is a vast subject and a lot of techniques which are already used in high energy physics, although in different contexts. We can find point estimates of the maximum posterior using expectation maximization. We could use variational inference for approximate fast and analytical inference, and we can use Markov chain Monte Carlos, which is a very common technique for exact numerical inference. Because we have a very simple model where everything is multinomial and Dirichlet, we are able to write a Gibbs sampler in Python without the need to resort to dedicated software, and which performs fairly well. So that's what we did. The Gibbs sampler is a way to obtain T independent samples of the parameters drawn from the posterior. Using these samples, we can approximate any expected value under the posterior distribution by the mean over the samples, and we can plot the marginalized distributions simply by drawing histograms on the relevant parameters. And so to obtain these samples, we only need the conditional distributions of each parameter conditioned on the other, which is really simple in this case because we only have multinomials and Dirichlets. Because the Dirichlet is the conjugate prior of the multinomial, every has a really simple shape. So what we do is we only need to perform for each iteration t, for each sample we are interested in, we only need the sufficient statistics to sample everything. The sufficient statistic is the number of measurements J and B assigned to class K, and it can be obtained merely by having the class assignments. Using this, we can obtain the number of measurements B assigned to class K, the number of measurements J assigned to class K, the number of measurements assigned to each class, and the total number of measurements, which is fixed. So what we do is we start the Gibbs sampler with a random event class assignment, we then forget about by taking the samples that are far away from the initial iteration. And using this initial class assignment, we can start the Gibbs sampling, which looks the following way. For iteration t, we compute the sufficient statistics with the class assignments of the previous iteration, and using the sufficient statistics from the previous iteration, we can have we can sample a value for pi, for alpha, for beta, and then finally for the next class assignments to consider. In practice, these samples are not independent from each other, so you need to burn in, that is, forget about a fixed initial set of samples and then thin the samples, that is, separate the samples you save by running the Gibbs sampler without saving the outcome. And if you do this, you can get more or less dependent samples. You can check by computing the autocorrelation of your chain of samples. And then once you have this, you can get a lot of information simply by because you have a posterior distribution. So you can have the corrected distributions of your data, of your parameters, which is what we are interested in. But you can also have an event by event probabilistic tagger, where you can marginalize overall possible actions and probability distributions for each class. So we implement this model using a simple benchmark, the case with a total 1000 total events with this true fraction of events. This is roughly a luminosity of 540 inverse femtobarns. We also tried with lower luminosities to study, and we used Monte Carlo samples obtained with MATGRAPH, PITIA, and DELFES as true data, and a smear version of this Monte Carlo as the thing we will consider as our Monte Carlo, that is our prior knowledge of the physical distributions. We make an exception for the signal fractions. We wanted to make things a little bit more difficult, so what we did is we assume no prior knowledge on the signal fractions, so we have a uniform prior on the fraction. So this is the two-dimensional distributions of our benchmark. They are not that different, especially in the number of widgets. We introduce a larger mismodeling in the number of light jets. We can see it by projecting into the one-dimensional distributions. True is the thing we will refer to as data, while fake is the one we will refer to as Monte Carlo. We introduce a large mismodeling for NJ, and we assume we have very good modeling on NB. We can worsen this, and it's still very good at reconstructing, but we wanted to reflect the physical situation where we don't know how to model the number of light jets properly, and the number of bit jets is more or less controlled. So once we perform Bayesian inference using priors given by our Monte Carlo, we can plot the corner plots in which we show the 1D histogram for every parameter and the two-dimensional correlations with every other parameter. Here we show in red our prior distribution. This is alpha 00, that is the probability of TTW for sampling the very first measurement of light jets, which is NJ equals 4 in this case. We see the true value in blue, and we see how our posterior is able to start from the fairly good prior but not good enough and correct the distribution and get very near the true value. And here we see the two-dimensional correlations between the probability of sampling NJ equals 4 for 4 tops and the probability of sampling NB equals 2 for 4 tops. We see here how the prior is very broad because we are assuming that we don't know much about the distributions. This is a scaling factor of 10. And this is a particularly good example where we are able to find correlations. We have this diagonal, which is very interesting because we are assuming initially that this is not assuming that NJ and NB are correlated, but that the parameters are. This gives a richer structure for the correlation matrix, which is fixed by the conditional independence hypothesis. So in reality, we have a lot of them. We can browse through them if you want. I'd be happy to, but this is the main thing. The corner plots are a lot of one-dimensional histograms and a lot of two-dimensional correlation plots. Here we see these that are not really nice to look at. It's because for high NB, the parameters for TTW are very small, so it's not nice to look at in the plot, but it works properly as well. So we can group together the parameters and compare prior and posterior for NJ and NB and for each class. We see that in general, what we're able to do is to reduce the dependency. We don't improve that much on NB, again, because we are starting with a very good prior, but we improve a lot on NJ. We reduce the uncertainty and we will get really close to the true values. And if we look to the fraction, we see that even if we start with a uniform prior, we are able to get something that makes sense fairly easily. Using this benchmark and a few others that we ran with different fractions, with different amount of events, we see that there is a good convergence and a good uncertainty reduction. We see that it's very easy to fix NJ because we have a lot of measurement of possible beams which are very populated, but that NB is harder and the fraction is the hardest. The limitations in the fraction probably reflect that we are making an additional hypothesis, conditional independence, which could hinder our capability of capturing the physical process. It also reflects the fact that the physical processes are very overlapping. That's why TTW is an irreducible background, because it's very similar to 4 tops, so it's harder to obtain the appropriate branching ratio, appropriate fraction of signal. But if we have NJ and NB simulations, that is parameter distributions we can trust, we can obtain the fraction in the usual manner, performing likelihood fits. Because the main problem really is obtaining the number of light jet distribution properly, we are doing really good in this sense, because that's what we are able to fix. So how do we evaluate whether our model works properly? Well, because in this case, we know the true values, we compute the log likelihood ratio of the current parameters given the prior and the posterior probability mass functions. We find that the posterior yields a higher log likelihood. We approximate and compute for each one-dimensional histogram separately. And in real life applications, we will not know the true values. That's why we are interested in this kind of algorithms. However, because now we have a Bayesian framework, we can compute, for instance, the Kubla-Kleiner divergence between the prior and the posterior, and we can measure the change given by the data. And we have a lot of other possible tests that we can use to evaluate whether our model is finding something or not. So to give a brief set of conclusions, we are able to model the data with a generative process, which is the key part of our work. This allows us to improve on Monte Carlo estimation by treating them as prior knowledge, which needs to be updated through event measurements. And so we are able to correct the number of light jet distribution properly. What could we do next? Well, we could use this to tune our Monte Carlo generators on signal regions. That is, if we have an appropriate number of jet distributions, we can use this to select a better tune for our Monte Carlo without the need of extrapolating from different control regions, as we saw before. And so we can have a better estimation of our Monte Carlo without introducing additional systematics, or at least not as large. We can also measure the signal cross-section, again with reduced systematics. We can test for new physics effects by looking at how the themes or topics or the recovered distributions look like. We can also test whether adding a higher number of possible class assignments yields a larger evidence and check whether this means that there are other physical processes lying around. And we can adapt it to other channels because the modeling is very simple. What we need to do is to write the generative process and then perform Bayesian inference. So that's all I wanted to mention today. I want to thank everyone for having me here, and I would appreciate any questions.
Okay, thanks a lot, Manuel. Are there any questions around? I don't see any raised hands. Let me have a look. Okay, in the meantime, I have a couple of questions. There is one general thing that worries me, is that even if at the beginning you said that you would keep things simple, at the end, things are not so simple. So since anything related to measurements is plagued by many kinds of uncertainties, I don't know how this could in practice work. At the end, you want to predict better the shape of the distribution of the jet multiplicity. How does this framework compare to what experiments do?
That's a very interesting question. I think that if we want to really be able to compare with what experimentalists do, we will need to be a bit more sophisticated on the generative process in order to keep track of also of the different nuisance parameters that they have. We can make it a little bit more complex. But the thing is that what we want to keep simple is the need for validating using other regions, other kinematical regions. That's why we want to perform everything on the signal region. So that's the main advantage of the model. I agree that we are neglecting some of these uncertainties. We are only considering one background, which is also an approximation. But I think if we included a bit more general generative process that keeps track of some of the nuisance parameters, maybe using a Poissonian distribution and the gamma conjugate, when we want to generate, for instance, here we are assuming, for instance, that the fraction is generated with a Dirichlet, and it's a multinomial. We could also say that the number of jets of models of events from each class is generated by a Poisson. This Poisson has a rate that is controlled by a gamma distribution. We can say a lot. We can introduce here in the prior knowledge a bit more sophistication. But I think that the main advantage is that we are not using the Monte Carlos to perform likelihood fits. So we are not overfitting to the data. If we have a relative size of the prior and that is able to keep the data in track, we should be able to keep things controlled and have a more controlled environment where to perform analysis. I don't know if I answered your question.
Yeah, more or less. But no, my concern is imagine you want to sell this to experimentalists. I mean, I put myself in the place of an experimentalist, and also no. This is too complicated. Just to put you an example. Even with the simplest multivariate analysis, once there is some discrepancy, they ask for a cut and count analysis that can somehow check it. It happened already in round one. There was a 3 sigma excess in multileptons, 3 leptons in a SUSY search. And the analysis was for 2 years delayed because they had a 3 sigma excess in something which could be SUSY, could be chargino, neutralino production. And then they held it until other team checked that, and they also checked with a count and check everything. So imagine you present people with a thing like that. They will say, okay, if I do this and I obtain something which is not exactly a standard model, it can stay forever.
But here, that's a very interesting case. But here we are performing a cut and count analysis. We are cutting on the events, and then we are counting only the number of light jets and the jets. That's why it's so simple. So but you cut and count also with a neural network. At the end, you cut and count. You put a threshold to the neural network and count. But here, if you did your traditional cut and count analysis, right? You can compare. You can compare, for instance, if you trust your Monte Carlos, but you don't trust them that much. That's why you are doing here. You can do the traditional analysis with your Monte Carlo. You can use your traditional analysis with the posterior estimate mean values that we have here, and then you can check whether it's different or not.
Yeah, that's a good idea.
Yeah, it is another ingredient to compare. If you see the very first transparencies Manu showed about Atlas, how they changed the number of jets by adjusting something. I mean, at that point, anything is better than that. But the interesting thing, I think, is that you only need to use from the experimental side number of jets and B of each event. You only give to the algorithm that, and it returns you what the algorithm infers to be the number of jets, the number of B distribution of signal and background with uncertainties. I mean, you use that just to, I mean, it would not be your only source of trustable thing, of course, but just to say, okay.
Yeah, what I mean is that in this case, you have a very, you can take the mean values and then perform it like you had a better Monte Carlo and then check the difference in the analysis. And also you can use take advantage that now you have for instance, a Bayesian framework. For instance, this is what I wanted to talk about when I said, for instance, you have an event by event tagger. In this case, sorry.
Yeah, I understand what Antonio says. Juan Antonio says that the mathematics is very complicated, I think, yeah. But it's not a neural network that you don't see what's going on. Here you see it.
I mean,
I
think
think
that
no, I mean, he made it very complicated to show all the details, but the truth is that it's the only Bayes theorem. It is only Bayes theorem.
Yes.
and I choose here I use the more simple, I don't know if the more simple, but one of the simpler Markov chain Monte Carlo algorithms. The experimentalists know way more about Markov chain Monte Carlo than I do. And they could use it way more efficiently than I do. I don't think that the problem will never really be the inference procedure, because the experimentalists are way better at implementing that I am. The thing is, we need to believe that we're doing something that works, something that's proper. And that's why we need to validate whether the posterior has makes sense or not. That's why we can perform, for instance, the KL divergency between the prior and the posterior. You can use some cross checks. You can use some.
Yeah, and also you can compare the distribution you get with a distribution obtained tuning the parameters in PCR like they do.
Yes,
things like that.
Exactly, that's the idea.
Maybe what you can do is, once you have these posterior distributions, you can tune your background to match the posterior distribution of the background, and maybe you can get both convinced of the posterior and convinced of the distribution, and you didn't need to resort to any control regions. You can also test this in control regions as well. You could do that as well and see if it works.
Let me say it in other words what Manu just said. He said, like, tuning the Monte Carlo in signal region using background cluster. The unsupervised method will cluster signal and background in signal region, which is 2 lepton semi-sign plus, right? You have some background and some signal. This unsupervised method somehow clusters background and signal, and you can tune it with background in signal region. Because you have the distribution of, you can retrieve the distribution of background features in signal region. Not the background itself, but the distribution.
Mostly I understand that you input distributions for 2 processes, say background and signal, and compare to what you make a prediction, compare, and then you tune your predictions by steps.
You can also run it in full unsupervised mode and see what you find, because you can use an informative priors everywhere. It won't perform as good, probably. Also, you could introduce, you can do an scan on the confidence you have on your priors to see what happens. Also, there's an advantage here, I think, in line with what we discussed previously before we started the talk, is that it's easier to see when this fails than with neural networks, because you have a probability distribution, you can see if it gets weird, you can perform some tests on known parameters. So and it's more interpretable than it has both larger accountability, and it's more interpretable than other methods which use deep learning, and which you don't really know when it fails, and you don't really know how to incorporate the systematics, how to incorporate the other statistical errors, and you don't need really a huge Monte Carlo to train this. If you had a relatively small Monte Carlo sample, you can introduce this with a large variance because you don't trust it as much. You don't need these very expensive Monte Carlo samples you need to train a deep neural network.
Okay. There is a small point that I noticed when you said about the conditional independence of for the number of jets and the number of B jets. I didn't understand it very well. Why you do that? I think it was this one. you factorize.
Yes, because we are dealing with multinomials here, it's not like a mixture of Gaussians where you have a very constrained shape of your distribution.
No, but what I don't have it clear is the left equal sign.
Ah, left equal side. Yeah.
Yeah.
What I'm saying is that when I'm conditioned on this latent variable, these two measurements are independent. So it's the product of the probabilities.
But I'm not sure they are independent. Imagine
no,
you
it's
have
an approximation. It's an approximation. It's and that's why you only take them to be conditionally independent.
Yeah, because you have a. I mean, you can have big quarks that are not tagged, and then they go to one side. I mean, the two. I don't know to what extent this approximation is correct.
Yeah,
because imagine
sorry, yeah.
Imagine you have 10 jets or whatever. Then we have an event which says no, 10 is too much. 8 jets. And you have 4 big quarks and 4 light quarks. Then if a big quark is not tagged, then it's -1 in the B and +1 in the light jet. So the probabilities are not independent.
Yes, you're right that they're not independent.
But you have to compare.
I completely agree. The thing is that what we are doing, we need to do that in order to be able to make it to make it find the mixtures. That's what we did here. So if we write it in this way, we force it to learn the mixtures, and we try to focus only on the correlation here. And this is where using a Bayesian framework is also useful, because if you look into the two-dimensional plots here, you can see that even if the measurements are not correlated given a class assignment, the parameters which dictate the measurements are correlated. So the correlation matrix, when it has a probability distribution, because now the parameters have a random variables, so you can have a fairly general correlation matrix which tries to capture the correlations through the mixing. That's the trick.
Okay, I don't know the details. You know better than me, of course. It's
an approximation. That's why it can also fail. I agree. Because it's a clear approximation. We know they are a bit correlated, like the light quarks and the jets.
I think that what Antonio means, is compared to what is this approximation, because of course it fails, but the thing that signal and background are so different, the distribution of jets and bees, makes that approximation it is valid, because the signal and background are still more separated in the distribution of jets and bees. That's to what you have to compare.
If you think it in this from here, we try to capture the correlation, but only through the mixtures. That's the magic. And then we will have additional structure if these two are also correlated when we treat them as random variables. So it's like another level when we go to the Bayesian treatment. If we think this as fixed parameters, the only correlation comes from the fact that we have more than one class. But if we treat them as random variables, this has also a distribution which will be dictated by the correlation between these two. And so we could marginalize over all possible values, and then we will have a really rich structure even in that case, probably.
Okay. Now, let me have a look if there are more questions. Are there any more questions? Okay, in that case, let's thank Manuel again for his talk, and see you some other day.